Mohammed, you're on mute, sorry.
Okay, sorry guys. Welcome to the fourth Pros Media Tea Time Talks. With this webinar series, we want to give junior researchers working on Pros Media the chance to present their work to the scientific community around the world. This is meant to be complementary to the geoscience and geoenergy webinars, which you can find in our featured channels, as well as to the Interpro conference, which will take place online this year. I am Mohammed Muraipur from University of Oslo, and I am here today with my co-organizers Maya Ruker from Imperial College, Kamal Singh from Priyotwad, and Tom Boltgrace from Ghent University. Another member of our team is Marcel Moura from University of Oslo, who cannot join us today. We do vary the time of our talks to accommodate speakers in different time zones across the world. Because of unforeseen circumstances, the second talk of today unfortunately cannot happen. Now we move on to the presentation by Samuel Jackson. Sam is a research scientist at CSIRO in Melbourne, working on multi-phase flow modeling, lab and field experiments. He is part of the research team developing CO2 monitoring techniques for stage 3 of the CO2 CRC Otway project. Previously, Sam was a postdoc at Imperial College London, working on X-ray CT imaging of multi-phase flow, modeling, and upscaling. Today, he's going to talk about geological CO2 storage and pressure tomography for CO2 plume monitoring. Thank you, Sam, for joining us today, and the floor is yours.
Thanks. Hi, everyone. Thanks for tuning in. So I'm calling in live here from Melbourne. So today I'm going to talk about pressure tomography for CO2 plume monitoring. And this is specifically in relation to the Otway Stage 3 project, which is funded by the CO2 CRC. So really, I have to thank first my co-authors at CSIRO who've developed a lot of the science behind this over the years before I even joined CSIRO. So James Gunning, Jonathan Ennis-King, Charles Jenkins, and Tess Dance. And then also the operations and subsurface managers at the CO2 CRC itself, so Paul Barclay and Mohammed Bagheri, and without whom it wouldn't be possible, this project. So the Otway Stage 3 project, it's the third incarnation of project at the Otway site, which is an onshore field testing site for CO2 storage. It's located in the state of Victoria in Australia. And the first two stages were really to demonstrate storage in a depleted gas reservoir and in a saline aquifer. These were really successful projects. There was a great amount of science that came out of them. And the Otway Stage 3 project is really looking to build on these and demonstrate safe, reliable, and cost-effective subsurface monitoring of CO2. So it's really about the monitoring and verification methods and really doing that in a cost-effective way. So specifically, the aim is to inject 15,000 tons of CO2 into a really well-defined, well-characterized saline aquifer and track the migration of the plume via monitoring wells using novel subsurface technologies. Now, the CO2 is to be injected in 3 stages of 5,000 tons, and at each stage there's going to be various monitoring techniques deployed to track where that CO2 plume is going. So we have a new well, CRC3, which is drilled 1,500 meters into the Parati Formation, which is the primary well for injecting CO2. There's then 4 monitoring wells, CRC4, 5, 6, and 7, which are deployed with distributed acoustic sensing, distributed temperature sensing, as well as standard pressure and temperature gauges. Now, there's 2 main forms of monitoring modality, really, that's going to be used on site. So the first is 4D vertical seismic profiling. And the really novel thing here is it's using permanently deployed surface orbital vibrators as well. This is going to be anchored to traditional surface seismic, so using a vibro-sized source and then a buried geophone array, as was done in stage 2. Now, alongside this, the other main modality is then pressure tomography. And this is using the pressure measurements at the monitoring wells with both passive and active pressure sources, as well as the earth tide response. So today, I'm really going to talk about pressure tomography using an active pressure source. So what I mean here is that we generate a pressure response in the field due to fluid injection, and we monitor that pressure. And that pressure allows us to have some characterization of the aquifer properties or CO2 if we inject CO2. So as an example here, here's a permeability field in 2D, and there's wells spaced at 300 meters apart. Now, if I inject water at well 1 here for 6 hours, it's going to generate a pressure response at all the other wells. And you can see the permeability is centered around a Darcy in the domain. If you monitor that pressure at the other wells, so you see at well 2 and well 3 here, you see the pressure at well 3 after 6 hours is higher in magnitude than at well 2 because of this high permeability region. If you look at well 5, you see the pressure is delayed, the actual response time and the travel time, because it's going all the way through the aquifer here, 600 meters. And then the actual magnitude of it is also reduced. So these pressure responses tell you something about that field and the permeability distribution in this case. Now, if we introduce CO2 into the domain, so we have CO2 centered around CRC4, which is given by this circle here. If we do the same water injection at well 1, you can now see that the pressure response at these monitoring wells is quite heavily reduced because this CO2 acts as a sink for that pressure. There's a reduction in diffusivity. Now, the difference at well 2 and 3 is quite significant, but the reduction at well 5 is really large as the pressure pulse has to travel all the way through that plume. So this really tells you where the plume is and can be used, just this pressure data, to invert for where that plume might lie. And the key thing when you're doing CO2 inversion is that repeat signal. So the water injection after you've got CO2 in place minus the water injection before you have CO2 gives this negative pressure difference. And that is really the impact of having CO2 in the domain. So how do we actually do this inversion then? Well, it all starts with a forward model, as most inversions do. And this forward model is to track the pressure propagation in a heterogeneous aquifer with a slowly varying thickness. And this is depth averaged through the thickness of the aquifer. And this is often done in flow models when you have a very long, thin aquifer. And the model essentially interpolates between a single phase case where there's just water and the pure gas case when there's just CO2 in the domain. So we have the pressure, P here, and which is influenced by the diffusivity in the domain, which is this permeability viscosity function, and it has a height in there because it's depth averaged. We then have a porosity, which is the porosity and height function. And then this middle term is the term due to any gas in the domain, which becomes highly nonlinear because there's another pressure term. And this really is impacted by the compressibility of that gas. So for any small amount of gas in the domain, this will dominate in that region. And what this allows us to do is model the pressure response for spatially varying diffusivity, phi, and saturation in response to an injection flux Q of water. So if we know the pressure that we're getting in the domain from an injection, we can actually do the inverse process and try and find out what these parameters are based on that pressure response. And we do that in a Bayesian sense. So the baseline data, when there's no CO2 in the domain, allows us to invert for that diffusivity in phi. Now the repeat data allows us to take off that diffusivity in phi component and just invert for the saturation. And what it essentially boils down to is minimizing the fit between our inverted model and the pressure data that we have from the field, including any prior information. And this is the Bayesian part of it where we have a prior. So we minimize this error function, which is the misfit between the data, which is our model pressure data and the field data, and the prior misfit, which is our current model and any prior model. And we take the derivative of this error function to actually update our model parameters in a Gauss-Newton approach until we find an optimal model which fits our pressure data. And that then ends up with an optimal diffusivity, phi, and gas saturation in the domain, which allows to match that pressure. So this is a very broad overview of the process. There's a lot of numerics that goes on behind the scenes here, and that's really detailed in this paper by James Gunning et al. In the International Journal of Greenhouse Gas Control. So I'll run through some examples. So the first case, we're going to look at a synthetic baseline inversion. Now, as with all inversion methods, really, you need to show that they actually work. And this synthetic case tries to do that. So we have a synthetic permeability field, much like the one I showed before, where we've got a number of wells located. And we're going to generate pressure data using an eclipse simulation. So we're not actually using our inversion model to generate the data here. We're not doing a full inversion crime, as it were. We're using a different modeling tool. And we're going to inject 150 tons of water at well 1, then at well 4, well 5, well 6, and well 9. And we're going to monitor the pressure at all of these wells. And that gives us these typical pressure response curves that you see. So this is from the injection at well 4. We have the pressure response seen at well 2, 6, and 7. This pressure data we can then use to invert for what this permeability field should look like with our model. So when we do that, we end up with these results. So the pressure data for well 1 and the monitor data is shown here on the left-hand side. The squares are the experimental data, and the circles are inversion response. So I say experimental data, I mean the data here from Eclipse. And you see it's essentially a very good match. It's almost perfect. And to get this fit, we've had to vary the permeability. And our optimal model is shown on the bottom right here. And you can compare this with the true permeability, the fine scale one at the top left here, and a slightly coarsened version of that on the top right. And we've coarsened just to make the numerical inversion slightly quicker here because it's quite a complicated, a heavy computational process. But you can see we pick up areas of low permeability really well from the inversion, and also areas of quite high permeability. And the inversion error within the well sort of radius around well 5 is within 20%. So with this synthetic case, you can see that we're able to actually back out what a spatially varying field should look like just based on the pressure data and really quite sparsely arranged wells that are sort of 300 meters sort of separation. So the next example I'll show is one with actual field data. So late last year, when the monitoring wells were installed on the actual field, when they were perforated, there were various injection and production tests performed, which you typically do when you install a well to check communication across the site and the general performance. Now, whilst these tests were carried out over 6 days, we actually monitored the pressure at well 2. Now, this is the well that was previously drilled for other operations from stage 2 at Otway, but it allows us to see what the pressure response is for these various tests. And this pressure response is the pressure difference from equilibrium, so from the starting point when there's been no perturbation. And we have various flowbacks at CRC4. You see an injection at CRC4, a flowback at CRC5, and another flowback, and then a flowback at CRC7 and at CRC6. And these injections, you can see they range from about 2 to 4 barrels a minute, and they last for several hours each one. And that creates quite a complex pressure signal that we see at CRC2. And we can use this data to try and invert for what our spatially varying diffusivity and phi in the field should be. So with this case, the true field case, we need some prior information to help us. So this is a step further than that synthetic case I showed before. So we have the obvious things that we need, so the flow rates, the timings, and the well locations. We need the pressure data, which we have. We then need a grid discretization covering the field site. The other thing that we need is any prior information from the field that might be able to help us. So any noise or covariance estimates on things like likely correlation lengths, which might help us with that prior, any known faults in the field, and any CO2 that actually exists already in the field. So these three are really summarized in the figure on the right here. This is a really simple depth averaged prior model for the field, really, and is based on a lot of the work that went into stage 2 by Tess and Stas, which is in these journal papers down here. And what we have is we have the well locations, so well 3, 4, 5, 6, 6 and 7. We also have well 2, and we have the CO2 plume around well 2 from the stage 2C operations. Now this is the plume contour and the depth average saturation from a seismic image that was taken during the stage 2 operations. This dashed line is the fault in the domain, which has been interpreted from this test period and previous geological characterizations. So all of this information really helps us build our prior model and gives us some information that can help us with our inversion. So we use this prior information, we use the pressure data and the flow rates, and we then try and match that pressure data and estimate what our spatially varying diffusivity and essentially porosity fields would be in this domain. And in doing that, we get the following results. So we have on the left the inverted phi, which is this porosity thickness term, and on the right, the inverted diffusivity, which is the permeability height term. Now these are non-dimensionalized. They're scaled around the average for the field. So that's a porosity of 0.2, a permeability of around a Darcy, and a thickness of around 30 meters in the depth. And what you notice here in these models is you see there's a high permeability region, essentially between wells 3 and 4, and well 5 as well, and a reduced region between well 4 and well 6. The other thing to notice is that there's no information past this fault. This is a ceiling fault, and pressure doesn't propagate through it, at least for our interpretations at the moment. And you also see as we extend far into the domain, we get less information, and we essentially back out to the value of 1, so the average properties, because we don't get any information really far from the wells as the pressure diffuses. But these models allow us to actually see what the pressure data is at well 2. So using those spatially varying diffusivity and phi maps, the red is the pressure we predict at CRC2 from this. So you see we get a really good match of that really complex composite pressure data. And this is due to the fact we varied the diffusivity and phi spatially in an optimal sense to give us that match. And it's not possible to match this pressure data without having this heterogeneous aquifer. And this is really key then, now when we come on to do the repeat test for CO2, because we want the repeat to only highlight really the CO2 that's in the domain, not any variations due to the diffusivity of the actual aquifer itself. So we'll now do a CO2 inversion. This is the last example. Unfortunately, we haven't actually injected CO2 yet into the real field, but I'll sort of do a halfway synthetic and real case to show you what this can do. So we're going to use the inverted diffusivity and porosity from before that we just got in the field, and we're going to use Eclipse to actually generate a plume around CRC3 here. So this is after 5,000 tons of injection, and this is what we might predict from our actual field case. And with this CO2 plume and the model here, we can then perform water injections at CRC 4, 5, 6, and 7. And we do this before there was CO2 there, and then afterwards there was CO2 there. And subtracting those, we get a difference in pressure. And that pressure difference is shown on the right here. And the response is negative because the CO2 acts as a sink, and the diffusivity is reduced and the pressure doesn't propagate as well. So this pressure data tells us something about where this plume is, and we can use that to try and invert for where the plume should be. So we've used Eclipse to generate all of the data, and now we're going to use our inversion methodology to try and match that pressure data and predict where the CO2 plume should be. So given that, we get the following results. So on the left, I show the prediction of where the CO2 plume is. The green is the depth average saturation predicted from our inversion model. The red is the actual plume contour from Eclipse. So you see, we've placed most of the CO2 actually within the plume contour from the Eclipse simulation. And that has resulted in a fit to the pressure response on the right here. And you see it's a really good match for that pressure signal. And that reduction in pressure is due solely to this CO2 that's in place around CRC3. So this was after 5,000 tons of injection at CRC3 of CO2. We can then increase that to 15,000 tons. So we get a new plume now, this red line from Eclipse, and we repeat the water injections, and we can again invert to see where that plume should be. And here the green is again our inversion result. So you see we place most of the CO2 inside that stage 3 plume contour from the Eclipse simulation. You see the pressure response now is even further reduced because there's more CO2 in the domain. So if I just go back to the 5,000 result, and you see when we've injected 15,000, you see the further reduction in pressure that we get from this repeat. Now, there is a slight halo around the north of the model here, you see, where we've also predicted there should be some CO2. Now, this is a sort of consequence of the setup we've got here and the symmetry in the domain. Because there's a fault, a known fault, acting along here, we couldn't really place any wells to the south of that because there wouldn't be communication over that fault. So the wells are all placed on the one side, and therefore there's a sort of symmetry with the injections that occur in this fault. That means there could be, from the actual inversions, some CO2 here. So you can remove this halo through extra constraints in the symmetry. But the key thing to take away from this really is that we can actually locate the CO2 plume primarily around where it has been injected. And we get a good prediction of that using just the pressure response from these monitoring wells. And there's only 4 monitoring wells here. We're not using any data from well 3 or well 2 here. And this can be done in a repeat sense as much as we like, really. As long as we have water on site, you can repeat the injection and redo the inversion and see where the CO2 should be. So this provides a really effective method for locating a CO2 plume. And I should say, we've used 4 wells here. You can take this down to just 2 wells, and you can locate where the sort of origin of the source is. And you can't do the sort of tomographic mapping as you can as you get more wells in the domain, but you can have some sense of where the CO2 plume is. And this is really important for conformance and demonstrating that you know where the CO2 plume actually is, even without having seismic information or things like that. So really, in conclusion, it's been a very quick presentation, but we've demonstrated pressure tomography, how it works, some of the theory and modeling, and provided some examples, and really shown how it can be used as an effective method for site-scale CO2 monitoring, and also for aquifer characterization. The more wells you have, the better your characterization, but in the very limiting case of you only have 1 or 2 wells, you can still do a lot with the actual monitoring and location of the CO2 plume. So the actual future plans, we've done a few baseline water injections so far, and we've done a fair bit of characterization. This was initially delayed due to COVID-19, but is now fully operational. A lot of the sensing is actually remote. And the CO2 injection is planned for later this year and at the start of 2021. So I think I will end the presentation there. I will thank the government, industry and research partners that are involved in the CO2 CRC and this stage 3 project. And then I will thank you for listening and take any questions. So thank you.
Thank you, Sam, for this fantastic talk on pressure monitoring of CO2 plume. We have a couple of questions. First is from Steffenberg. He says there's also this approach by Lake, who uses the correlation in well rate pressure fluctuations. How would that compare with the inverse modeling in terms of resulting uncertainty?
So we can, thanks for the question, Stefan. We can, this approach, essentially at the moment, and when I've demonstrated it here, we're doing a single rate test. But you can actually do multi-rate tests, and you can even do pulsed harmonic signals. And the generation of that pressure response is different, and you can actually pull out more, or I should say different information from the field. So the sort of combinations of different injection modalities can then really inform different frequencies and different spatial length scales in the domain. So you might do a very short injection or a very long injection when you're trying to uncover information about the different length scales of heterogeneity, at least from the aquifer characterization. And it's a good point as well to mention, Stefan, that a lot of this kind of testing has been done in the petroleum domain, at least when you have a single well and you just look at average properties in the domain. And it's also done in a sort of in a shallow hydrology sense, where they have hundreds of wells really shallow and they map permeability in 3D. I think the main thing here is that we're using an intermediate number of wells, and we're using it directly to detect CO2 and gas in the domain, which is the major thing here, because that induces a response and a change in diffusivity, which can actually be detected.
Thank you, Sam. And the second question is from Rihane Akbari. He says, very interesting talk. Since there are geophysical monitoring and geophones in place at CRC, do you get a good match between geophysics and pressure tomography for saturational phases? This is interesting.
Yeah, this is a very good question. So, I mean, that's the holy grail of seismic and geophysics, isn't it? Is getting actual saturations out. So there is a buried geophone array. There's also 4D VSP going on. So there's going to be seismic tomography done on the site to actually capture where the CO2 is. This really, you can't really get saturations easily from this. And that's because the gas or the CO2, the seismic response is so large that it's very difficult to detect subtle changes from variations in saturations. You have to build in sort of rock physics models to get those kind of predictions. And it's similar in a sense to the approach we've got here in the tomography. So I've got a depth average saturation here, but really it's a map of just where the plume is. The gas causes such a response in the domain that you can track the actual contour of where it is, and you have it in a sense over the height of the reservoir. But quantitatively comparing the saturations with geophysics measurements is very, very difficult. What we'll be looking to do is comparing the contours and the footprint of the plume with what you get in a geophysics measurement. And I should probably say as well, with the geophysics, it is there's the barogeophones, there's the 4D VSP, and all of the traditional seismic going on to verify all of these methods.
Thank you, Sam, for this explanation. We got another question from Niloy Day. Thanks for your talk. Did you consider dispersion in your model? He wonders the pressure reduction may happen due to transversal spreading of the plume.
Yeah, so we essentially consider that, if I go back to this equation here, we don't really consider dispersion on the large scale. Really, it would be lumped into a effective diffusivity, a permeability sort of viscosity term here. And so really the pressure propagation, it is flow, but we're talking about the pressure here, is really impacted by that diffusivity and that porosity. And it's not like we're injecting a tracer here that's going along the flow path and is dispersing through the pores. We're looking at the pressure propagation at a much larger scale, which is really just impacted by these large scale variations in diffusivity and porosity.
Thank you, Sam, again. We got another question from Riane. In complex saline aquifers with heterogeneity and anisotropy, detailed characterization of reservoirs is difficult. With low number of monitoring wells, how accurate pressure monitoring will work?
Yeah, okay, that's a very good question. And we've done a lot of sensitivity analysis on this, on sort of like how many wells you can get away with and what you actually need to characterize. And I should say, we say tomography here. That's maybe a bit of a cheat in some sense, in that with these low number of wells, it is really hard to get spatial information at fine resolution. So when we have the wells separated at, say, 300 meters to 500 meters, like they are on site, you can get information at sort of the 100 to 200 meter range. But it's very large scale and quite sparse. And that's not at obviously there's much finer scale features going on in the aquifer. And so what we're measuring is sort of large scale features that are upscaled averages of those properties. And one of the things that our prior model can do, because we're doing this in a Bayesian sense, you can weight the prior model to certain extents. And we have detailed information at the wells of permeability, porosity, the formation thickness, which really does constrain a lot of the model. And when you add that in with other measures, so when you have seismic and you can pick the horizons, you have other sorts of measurements coming from those actual well data, you can quite nicely constrain, at least at the wells. And that just builds in some confidence into your mapping. And then the mapping itself is quite a large scale. So one final thing I'll add to that is that we are building into this a step where we essentially downscale this information to our geological model. And our geological model, which is primarily built by Testance, is a really detailed fine scale model of the Otway Basin. And we can then compare the different scales of permeability and such across these different measurement methods.
Thank you, Sam. There's another question from Stefan Berg about slide 11. So do you actually get information outside the circle spanned by wells 1 to 9?
Yeah, so we do get some information outside, but it's hard to trust a lot of that information because the pressure is propagating much further than these wells. And really you want to use the cross well information. That's the most accurate. And what you see around the outside of some of the wells is a sort of halo effect from symmetry that's introduced because we're using Green's function here for the pressure solution for a lot of it. So that's a sort of uncertainty that I wouldn't really want to bet my house on, as it were. Yeah, I hope that answers your question.
Thank you, Sam. There are no other further questions. I have a quick question. It's a more general question about the costs and economics. So, what's the overall cost of the project here?
But I'd go as far as say it's quite a few million for the whole project. But this is an onshore. I'd say generally with the so I should say that number is very vague, but there's all sorts of things going on in this project with geophysics and all that kind of stuff. When you're using monitoring wells, onshore drilling a well is not that expensive in the grand scheme of projects. So you can get away with drilling multiple wells. And so that's what this is really intended for. When you go offshore, it becomes very expensive to drill a well, and you might only have one monitoring well, say, and you'd place this quite far away, so you're definitely not going to interact with your plume. And that would be then using this in the most limited sense, where you're just trying to pin down the rough location of the plume. You do get some projects where you do have lots of monitoring wells. So the Gorgon project with Chevron, they have a lot of wells surrounding the CO2 plume. But for this, really, for the economics and things, it makes sense for it to be more based in an onshore location, I would say.
Okay, thank you, Sam. Thank you for the wonderful talk and for a great discussion. It was a pleasure to have you in our studio. And Stefan also say thank you for the great talk.
Thank you.
Okay, so due to some unavoidable circumstances, we don't have the second talk of the day. Our next talk will be in 2 weeks. It will be given by Alessio Scanziani from IEA and Berzan Primkolov from MIT. Alessio will talk about three-phase flow in porous media, and Berzan will talk about extension of the Linomore phase diagram. Please join us in 2 weeks for these talks. And finally, I would like to thank you for your wonderful comments and feedback, which always helps us to improve our YouTube experience. And if you have any comments, any feedback, please do send us on porosmedia@gmail.com. And if you like us to add you in the mailing list, please do send us an email on this. So thank you again for everyone for joining us and for putting all the comments. And we'll see you in 2 weeks. Take it. Bye. Thank you, Sam, once again.
Yeah, thank you for inviting me. Cheers.